as you can see, I changed the name of the title. So when I originally came up with this project, I originally named it I'm the Hunter, because I was listening to Bjork at the time. That was the song that was on, and I thought I was being clever. Except nobody knew that I was actually talking about a Bjork song, so I just sounded creepy. So I figured I should probably change it. And as you'll see, this probably is a really fitting name, especially if you're familiar with Oprah in the United States. You'll see why in a minute, but we'll just go ahead and kick it off. So, as Thomas said, I work for iSec Partners out of San Francisco. I've been based out of Denver for quite a long time, but we have offices in San Francisco, Seattle, and New York. But we're a consulting firm. We've been around for quite a few years now, I think 6 years total. We were recently acquired by NCC Group. So overall, we do security. We attempt to write exploits, but mostly we just consult. So that's the obligatory I have to tell you about my background slide. So let's just jump right into it, okay? So I have to talk about the places that I've been in the past 24 hours, which apparently has been a lot of places. Can you see that okay? Yeah. All right. So I started out in Boston. Here I am, happy in Boston. And you can see that nice little circle around me. I'll get to why that circle is important later. But I jumped suddenly to Afghanistan, and then even further to Libya. And then for some reason, I was in the middle of the White House, which was awesome. Nobody knew I was there, of course. But really, like, what is this all about? Okay, so you saw some of the names up there in the previous slides, right? I mean, obviously, I didn't go all these places. I'm spoofing, right? What am I spoofing? I'm spoofing my location using this awesome little tracking device called a zoom back. Not many people even heard of this thing, but it's a very important device for many, many reasons. And here it is, right here. You can see it's extremely small, okay? In fact, I'm gonna pass it around to you guys just so you can get a better view of it. Open it up and take a look at the contents inside, because you'll find that it's extremely simplistic. So I encourage you to actually, it's already unscrewed and whatnot. But it's important to get to know what's going on inside, because these things are very powerful. As you can see, they're very small. So just to give you some background on what this device is, this is a GPS device, right? In the United States, it's sold in almost 13,000 stores nationwide, which is crazy, right? For a tracking device, you would never think that there would be a consumer-grade tracking device that you can just get off of the shelf in the United States, but you can, and it's kind of scaring people that you can do that. But you can now, for very cheap as well. It's only about $99 American. And it's, as you can see, only about twice as big as a Nano. So you're supposed to be able to track your vehicle, your family, your pets, and people are even using it to track shipments. If you've got, cargo loads, medical equipment, things of that nature, it's going across the entire United States and you want to know where it is along that line of traffic, now you can track it, which is great. But at the same time, there are going to be a lot of problems involved in that kind of a tracking system, right? And Oprah in the United States is a very big popular name for anybody that wants to get something pushed out. Basically, in the United States, if Oprah, well, how many people are familiar with Oprah and her unsettling power? Yes. Yes, very enthusiastic in the back there. You know how it is. Okay, so if Oprah says anything is good, people flock to it, okay? If she says that a book is incredibly awesome, people are gonna just buy that book and turn it into an instant bestseller. That's just the way it is in the United States. And she actually put this as number 16 on her top 100 things that are awesome in the United States, which actually significantly drove up their sales to the point where they got bought by another security company that was interested in tracking. We'll get back to why that's important later, but that's just an interesting tidbit to note. So we'll just talk very quickly about the internals of the device. So it's pretty much what you would consider to be a typical assisted GPS tracking device. So how many people actually know what assisted GPS tracking is, or how it works? Raise your hands. Anybody? Somebody? Okay, so here's the breakdown, okay? Assisted GPS tracking is where you're passing off the location data to a remote system, okay? So it's not just GPS, it's in your car or on your phone. Somebody remote wants to know where that device is, which means that the GPS device has to be able to send that data somehow back to another system. Okay? And that's the assisted part. Well, there are two reasons why it's called assisted. Number one, because the location information is being assisted upon, right? As in there are multiple sources of location data. And then two is in you're assisting an outside source, okay? As in you're trafficking that location data over some kind of transport to a remote location, usually some kind of server or an individual or something of that nature. So this device is composed of a GSM module, which is actually how it does two things, okay? First, it determines your cellular location. It says what cell towers are around me. I'll gather that information, get the signal strength information that's kind of half the location data. And then two, it's going to use the GPRS network to send the information back to a server, right? And then of course the GPS module, you're just getting latitude and longitude, in some cases elevation, and you're sending that of course back over GPRS. You've got a microcomputer, sometimes a microprocessor, in this case a microcomputer, that actually runs the application. And then of course your typical SIM card, which in this case is T-Mobile for this entire organization. So I'll talk a bit about the module because it's actually a very interesting module, especially for researchers. So the SyScan'11 is its own little, souped up GSM module all in one. It's got a little Skyworks RF transceiver, which is a nice little piece of hardware, and an Infineon baseband. And it's really interesting because you can't, typically in environments today that are, mobile environments today, you share memory, right? So you have an application processor, and you have a baseband processor. And those two systems together are usually going to talk over shared memory. The baseband processor is going to be the master, and then the application will be the slave. In this case, this is kind of old school, where you actually talk to the baseband over serial, and just tell it, hey, dial into this GPRS network, or call this phone number, or what have you. And then it sets up a voice channel over serial as well, on a different serial port. But the important thing to note here is that there is no shared memory, so everything is existing over serial commands, right? So it's old school, but it's a modern device. It's interesting to keep that in mind. The GPRS module is really standard, so I'm not going to talk about it. It's pretty boring. It's GPS. The application processor is actually quite interesting, but I'm not really going to get into it because I don't have to, and you'll see why. It's an SH from Renaissance, which if you're familiar with the Renaissance architecture for SH, they do a pretty robust job of actually being able to deliver some semblance of security architecture inside a small microprocessor. But it's a pretty cool platform. You play around with it a lot. It's great for actual production line quality stuff. But I don't really know what the application is. I assume based on things that I've captured over the wire and over GPRS that it's Java. But I don't really know. And I don't care, because I don't have to know. So this is why I don't have to know. So as I said before, the baseband module takes all the information over serial, right? So if I know that, all I have to do is hook up a logic analyzer. In this case, I just use SyScan'11, right? And I just sniff the TX pins. So I just watch, okay, where on the actual, who has the device right now? Anybody? Yeah, so if you look under the hood, where the baseband is, you'll see the 0682. You can actually take that off very carefully if you want to. There's a Molex adapter for it. What you can do is look right underneath. There are two little pads, and those tap pads are the TX pads for serial. So if I just tap that with the logic analyzer, and then I see all those cool little things at the very top, which is all AT serial traffic, right? So that's all hexadecimal up there at the top. And if you are familiar with these characters, these are actually ASCII characters in serial. So you can just watch the stream of commands go back and forth between the application processor and the baseband. So you know what the application processor is thinking, right? In which case, if you can capture all the data you need to over that, then you don't really have to care what's on the application processor or how it works. So just a quick aside, getting back to why this is a really interesting baseband. So there are a couple reasons why this is interesting. First of all, A52, right? So as many of you are probably familiar with, A52 is a deprecated encryption scheme for GSM. It's not supposed to be used anymore, and it's certainly not supposed to be put into manufactured phones anymore. This was actually enforced by the GSMA sometime, I think around 2005, and it was put into the 3GPP, I think, as a mandate in 2006, if I remember correctly. But A52 was not supposed to be used at all anymore. But the United States, this device is only capable of A52, right? So that baseband actually is using an encryption scheme that should not be present anywhere in GSM today, especially not in the United States, which we're apparently bleeding edge, right? But this proves that we're not. So this device itself can only connect to networks over A52. And when it does connect over A52, it's connecting over GPRS, which means that GPRS in the United States is capable of A52, even though it's not really supposed to be, right? Which is interesting in itself. So even though that doesn't really say anything about, well, you know, I'm not out there sniffing A52 right now, but it proves that I could be, right? When everybody thought, oh, well, I need to be able to crack A53 or something of that nature, one of the more difficult encryption schemes. That's not necessarily the case. If you find a vulnerability where you can force a device into A52 mode, then you're cool, right? Because as many of you know, A52 can be cracked in real time with pretty much commodity hardware, and that's been proven by cryptographers. So let's get back into how this actually works. So the zoom back itself is all about the customer experience, right? They know that many people out there, especially people that are going to be using this device, are not interested in the technical details. They don't know anything about GPS, they don't know anything about a GPS, and they certainly don't know anything about the cellular network. So all they want to do is just log into a pretty interface, click on this is my device, and see a map of where that device is currently, okay? And maybe even where it's been. So how does the device itself work, right? So as I mentioned before, it's a GPS, so there has to be a control channel for sending messages to and from the device. So how do you actually tell it where is your location right now, right? That comes over a particular control channel. In this case, it's SMS, where it actually receives control messages over text, which is really, really awesome because we all know that we can spoof SMS today. Yay, right? That's great. That makes it really, really easy to attack. So it's simple 8-bit binary protocol. And people that are familiar with SMS will know that all you have to do is set a couple of bits in your SMS payload, and now you're done. You have a binary message, and you can ship that payload to however many phone numbers you want. So the application itself just constantly polls over and over the SIM card for SMS messages and tries to determine whether or not those messages are intended for it, which means that it's parsing SMS somehow. And those messages have some kind of indication of where that message is coming from, where the message is going to, and some kind of identifier for what type of message it is, right? Here's what it actually looks like. So this is a little hex dump of a typical command that you'd see coming in over SMS. And this is really common. This is the great thing about the zoom back, because this is actually very indicative of how many projects are deployed, especially in the United States today. If it's some kind of embedded device that's unmanned, right? In a lot of cases, they're controlled very similarly with binary SMS. So this example, as you can see on the right-hand side, the actual text, right? On delocate, and then on loc 34, blah, 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 right? Those are the two main things that you want to capture from this little hex dump, okay? The first token, the on delocate token, actually represents an incoming request. So you can see that even though it's binary, it still has strings, it still has some kind of normal format that you would be able to reverse engineer very quickly, right? Then the location token itself is essentially just a nonce, right? It's just going to say, hey, here's this token for this session, pass this token back to me at some point later. And then this bit of hex at the very bottom here is actually, I determined after some bit of hacking that it actually is just an IP address. So it was actually quite silly because originally when I saw that it was A52 capable, I assumed, oh, it's not using GPRS at all. It probably sends data back over SMS. But I couldn't get it to do that over OpenBTS. I constantly was sending it messages. Why aren't you sending messages back over SMS? This is ridiculous. My formatting is correct. I even wrote a patch to be able to send messages over L3 because I thought that SMS was not being sent properly. In fact, OpenBTS itself doesn't correctly send binary SMS, so you have to tune it anyway. Actually, I think there's a fork or a patch right now that does it, but back when I did this, they didn't even have a patch at all. But once I figured out I was using GPRS with A52, it became very obvious that if you look here, 43CAED at the very last line on the right-hand side just seems to be out of place with the rest of the binary. So you kind of see right away that, wait a second, that's probably indicative of, oh, it's 4 bytes that look like something not random. That's probably an IP address, and let alone, oh wait, it is. And then simple whois will show you that, oh wait, yeah, okay, it's Zoomback LLC. So you can tell, right, the formatting of these payloads is pretty simplistic, okay? And again, this is really common among devices that are controlled over GSM networks. So the location request itself has very specific things that we care about. Defines where the device should connect, as in that IP address, and what the device should send, as in the nonce that we just saw, right? So what does the response actually look like, right? That's the next obvious step, of course. So we just go back to the logic analyzer. We just take out the Solea, and we say, okay, what do we do now? Just took up the same pins and initiate a session from the usual web interface, right? Dial into the web interface, click on Find My Application, and then actually intercept what that data is being sent to and from the baseband processor, right? And we say, okay, the response is being sent over AT. We just watch what the device does. Here's a session. Okay, this is actually pretty cool. So there are a couple things to note about this that make it quite interesting, at least to me. The AT commands back and forth are actually defining at the very top. You can see that it's dialing into a T-Mobile APN. Okay, it actually says CID AGPS T-Mobile.com. So every time you connect to a GPRS network, you have to specify an APN. And the APN essentially defines how you're accessing some kind of network infrastructure, right? So there are many different types of APNs, and different types of devices will be allocated specific APNs for specific functionality, okay? And that's really interesting because that means that certain APNs are going to give you access to data and resources that you wouldn't find elsewhere because they're partitioned, right? They're firewalled. They have specific controls, and they're usually using the SIM card, the authentication, using the SIM card, as a token to drop into these networks, right? So aside from that KI stored on the SIM card, there's really no other control that says, yeah, Don can access this particular resource, or Don can't access this other resource. It's just defined by your SIM card and the GPRS network. So what's interesting about that is I can take a SIM card that hasn't been allocated to a particular device and then say, I want to dial into this exact GPN or APN over GPRS. And it'll say that you're being dropped into that APN, but actually you're being dropped into the general pool, the general GPRS pool. And if you have significant authentication, you'll pretty much just be dropped into regular IP traffic, right? So you'll be able to access the internet, but not this particular resource. So the second cool thing to note, the highlighted region, is of course the IP address that we saw from the SMS control message, right? And that's awesome, because now we know a couple of things. Number one, that this device is directly accessing that IP over the baseband, right? Which means that, there's no shared memory, there's no TCP IP stack on the application processor, right? So it's going to be extremely easy to intercept all the messages going back and forth because they have to be handed off to the baseband processor over serial. That makes attacking this device extremely easy, right? So it's not like iOS or something of that nature where you have a more robust device. These are cheap embedded devices that are manufactured so that nobody ever has to interact with them once they're enabled. And that's good for us, it's good for the researcher, because it means there are fewer steps to take in order to reverse engineer and get what we need. And you can see the payloads here, right? So below you see a typical post in the middle of the page, and that post just goes to a particular location. And as you can see underneath it, there's simply just post parameters that essentially define, here's my location in some format, right? And then a little bit further down, you can see a second query, or a second post, with a little bit different information, but a similar format, right? but you can identify the location nonce in both places that was sent in the SMS payload earlier. So this is one interesting thing to note. There's obviously zero confidentiality, right? And TCP/IP is entirely on the baseband. So let's go ahead and break over to that real quickly. So baseband attacks that we've seen recently are an extremely serious issue, right? The baseband itself is usually very simple. I mean, it's a complex thing, obviously, because you're dealing with RF and controlling a transceiver. But it's also very simplistic in that you have a small application processor that's usually a microcontroller with a small amount of flash and a small amount of RAM and a small amount of EEPROM that allows you to define your application and control this transceiver, right? So the attack surface for these things is very high because the security confidentiality, or the security surface of these devices is very small. You can't pack a lot of security controls into an application processor like this because they have to be small, they have to be quick, and the processing on them doesn't have enough power to be able to implement things like ASLR, et cetera. Right? So they're very simplistic. But then when you put a TCP/IP stack on it, now you're significantly expanding your threat surface by saying, oh, now I'm going to be processing raw data over the internet. That could be anything from any source. And suddenly, you could have potential overflows from fragmentation issues, header offset issues, et cetera. Right? And that's a real issue. We've seen in the past, even in the Windows kernel, and even in the Linux kernel and the SCTP module, that remote exploits over TCP/IP or any other networking protocol can occur. Okay? And they can cause remote compromise. When you're on a small application processor, it's a very real part of your threat model. Okay? So an easy attack scenario for this kind of situation would just be force this device or any other device with this kind of a processor or proprietary functionality to connect to you over the GPRS network, to reach out to your network. And then you just simply exploit the TCP/IP protocol by interacting with it, right? That's really cool. It's excellent to know that we can do that. We hadn't really seen before that devices were capable of this. It's not documented anywhere on the internet. It's documented somewhere in proprietary, NDA, Infineon module stuff, right? So that's exciting because we know now that if we want to compromise specific embedded targets, those embedded targets are probably not going to be able to upgrade this firmware. They can upgrade the application firmware, but it's going to be extremely difficult for them to update the Infineon processor, which means that any TCP/IP exploits, now control the actual device itself because the device is always going to connect to the net over GPRS, right? That's very exciting. So now you know that there is at least an in, a possibility of an in, to control many, many different types of devices using this proprietary TCP/IP stack functionality, and you can own pretty much whatever you want to and ensure that you have a persistent backdoor by redefining the GPRS parameters and forcing IP addresses to go straight to you. It's a very real possibility. Okay? And I'm working on an exploit for this as well that I hope to demo at Black Hat, but we'll see if it's ready. If not, maybe I can actually submit this to another SyScan'. But let's go back to the payload. So you can see, obviously, I've just chopped this up a little bit so you can see the format, the structure of the message itself. So the highlighted line here just simply defines the actual cell phone towers that are around the device. So again, this is the assisted part of assisted GPS, right? You get the location by determining where are the cell phone towers around me. I know that there's a cell phone tower for T-Mobile, for Vodafone, AT&T, or whatever, and I know kind of where I am in relation to those devices by the RSSI, or the signal strength indicator, which is the last part of this, or the last field in the highlighted region. After the last ampersand, you can see the -57, that's the RSSI for that particular cell tower. So the cell tower has 4 different parts. The very first 4 regions specify the cell tower's ID, the location area network, the network code, and the country code. So those 4 things together define one specific tower. And knowing that one specific tower's information, you can use a database that you can get online, like OpenCell ID or something of that nature, to determine where that actual tower is. So of course, we just have 5 separate cell tower pieces of information that allows us, using RSSI, to pretty much get you an idea of where you're at within that region. So the whole payload itself, you can see, again, we had the knots, right? The very first thing you see up there, after my command, is the LOC34. That, again, from the SMS payload is the knots. Then you have, version information, a timestamp for when this data was sent, etc. The second response format is actually more interesting. It's the same format, except instead of cellular data, you would be seeing location data. You should be seeing a GPS coordinates. And that's something interesting we'll get into a little bit later when we get back to the spoofing that I showed originally, because you don't always see the GPS coordinates. And that's why it has to be an assisted GPS device, right? Because based on cloud cover, or say if the vehicle that you're tracking is inside a building, say a garage or something of that nature, you're not always going to have GPS data. So you have to use the assisted part, or the cellular data, to determine where is your location, when you don't have GPS information. So the second payload will sometimes not even contain a GPS coordinates at all. You'll just see blank information, which is okay, because we have OpenCell ID. So I mentioned it a minute ago, but OpenCell ID is essentially an open source library of all the cell towers in the world, right? It's not complete, but it's pretty darn good. And you can get information on cell towers pretty much anywhere, right? Especially the United States. So you can search through and say, okay, if I know all those 4 parameters, the country code, the network code, the location area code, and the cell ID, you can just search for those tokens inside the database and say, oh, this location is in Houston, Texas, or this location is in Singapore. And it'll give you that information, and sometimes it'll even show you latitude and longitude for where that cell tower is. And if you know where that cell tower is, pretty much exact location, and you know the RSSI, or the signal strength of the device between the device and the actual cell tower, and multiple cell towers, you can now approximate pretty much where that device is. Which, if you remember in the first slide, you saw that circle around the pin cushion in the middle, right? That red pin cushion is surrounded by that big circle because GPS data was not available, right? So it thinks that my location is the red pin cushion in the middle, and actually this is extremely accurate. Even though there was no GPS data, this was my exact location where the pin cushion was. But the AGPS data, because it's loose, right, it doesn't triangulate you to a specific point guaranteed. It shows that this is your particular region or your zone based on the information that we have. But it's great to know that even AGPS can be this accurate, right? So, obviously, we know how to control the device, right? We can send it information. We just send it an IP in an SMS, and we know exactly where that data is going to be sent to. We know what a response looks like, so we know when data is incoming from a particular device. We know how it's going to look, and we know how to respond to it. I didn't bother because it's not interesting, but you can sniff the other side of the serial back to the application so you know what the response from the internet looks like. It's just a bunch of zeros, so it's not interesting to look at. So I didn't bother you with it. But you'll also know the zoom-back server resides in 7276, which is actually a field defined in the SMS, right? So that's excellent. We know that we can control all these things, and we know exactly what network it's sent to by, again, sniffing the serial commands, right? So, what now? Aha! We're going hunting, finally. We're actually going to do something fun. So let's piece it together, okay? What you're going to do if you have a situation like this, and again, this is not the only device with this kind of capability. So what you can do is you can sign up for an SMS service like RotoMessage. RotoMessaging is awesome. They're my favorite SMS vendor. They allow you to script your own commands over SMTP, so you can send SMS over the command line, and you can even do it while spoofing your address, which is great. So you just simply build up your own script, and then start sending out the same SMS that you captured earlier over RotoMessaging, but you can kind of do this in mass, right? So you simply change the IP address to your IP address, And then you just sit there on port 7276 and wait for these devices to come to you. So here's my script. And you can get this in the slides, or online, it's in the slides, obviously. But it's very simple. You guys can probably whip this up in 5 seconds. But essentially, there are a couple things that I just wanted to ensure that were defined properly. The from is very interesting. It's 12060. They've actually changed it recently to 2232. But this is a short code internal to T-Mobile. So T-Mobile is not actually supposed to route this information or route from this source, right? But because router messaging is awesome, they somehow are getting that message through to T-Mobile as the correct source. So you used to be able to send messages to these devices from any address, any phone number that you wanted to, and it wouldn't care. The device would respond regardless. Now when you try to send a message to it, it only responds if you can actually send it from the correct source, which is the new 2232, if I remember correctly. But because roto messaging, again, is awesome, you can just change that field and you're good to go, right? So there isn't really much protection there. Obviously, even though the infrastructure side is trying to protect from these issues, it's not a sufficient protection because SS7 routing is allowing people to get around these issues or these mitigation controls due to whatever firewall solutions these guys are using being faulty, right? So there is SS7 firewalls that are supposed to block these things, but apparently they are pretty insufficient. So here is an actual payload, right? So I'm sitting on the GPRS network on the same device network, the APN, that these devices connect to. And this is an actual message from one of the devices to me. So the device actually reaches out to me and says, hey, here's my post data. And as you can see, it's the exact same thing that we saw over serial, right? So it's the exact expected format that we wanted. And you can see that it's a typical control message at the beginning. You see the three-way handshake, etc. So now we've proven that we can sit on the GPRS network and listen to incoming messages, right? We know we can intercept. But what does that really mean? If we can intercept, that's awesome, but you have to be able to find devices. I can't just find a tracking device anywhere, right? If somebody puts a tracking device under my car, I don't know that it's there unless I constantly look every single day for tracking devices under my car. I'm not going to know. So we have to define a way to actually find these things on the telephone network without them wanting, without them letting us know that they know, right? So I defined this little thing called war texting. So nobody's really been talking about war texting, but it's extremely useful, right? So war texting is essentially spam, which is why it's difficult to do correctly. But you just blast out your text message to thousands of numbers at a time, okay? But you're waiting for a response this time, whereas before, obviously spammers are just sending out messages to whomever trying to get somebody to go to a bar in Singapore. Whereas versus this is actually trying to trigger reactions from embedded devices. And we've proven that we can do it because of this little genius device here. So essentially, the reality of war texting is horrible, right? As I said, it's spam, okay? So because it's spam, you have a lot of problems in sending messages fast. If you want to blast out to thousands and thousands of different phone numbers, you're going to be in trouble. You're going to get blocked, and your peer is going to drop your messages. So it's going to look like you're sending data, but you're not actually sending any information at all. Nobody on the provider side is actually receiving any information. So you have to scale it back. And I've tuned it to the point that I understand that if I send one message every 20 seconds, which is horribly, horribly slow, you probably are not going to get dropped. But the cool thing about that is the cloud, right? So if we just set up EC2 servers where we can do this remotely, I can now have 5, 10, 20, 100 different SMS or SMPP accounts and just slowly crawl through the entire telephone network in the United States, iterating over thousands of phone numbers in a couple of days. But it only costs like a couple of seconds, or like what, 0.02 of a cent per message, something of that nature. So it can get expensive if you're doing hundreds of thousands of messages, but it's really not that bad. And there's also a better way to do it correctly. right? So you don't want to increment through SyScan'11. Like if your phone number, if the last 4 digits are 0000, you don't want to just increment to 0001, 2, 3. That's bad, right? Obviously that can be fingerprinted. People know that you're crawling through. So you just randomize between a specific set of numbers that you want to test. So I also devised a different kind of method called device profiling. So device profiling makes things a lot simpler, right? Because you don't really just want to iterate through phone numbers or randomize from a set of phone numbers. That's a waste of time, right? And you don't want to send 100,000 different messages to 100,000 different phone numbers if you know that 100,000 different devices aren't out on the network. If you know that your device share, you know, the Zoomback is selling at what, 13,000 stores. And they claim that they've sold 100,000 or more of these devices like in the past year or two, right? So you figure, okay, there are how many, you know, hundreds of thousands of phone numbers available in the United States. That means that the actual share that Zoomback has of the phone number real estate in the United States is probably really small, like maybe 1% if that, right? Probably much, much less than that because not all of those are going to be on at the same time, right? So we have to figure out how can we determine if a phone number, an actual phone number, is a device without you know, just sending it the SMS message. So we just set up a device profile for it, okay? So the device profile for the Zoomback itself is that incoming calls are disabled, right? So if I call it, I know that the call is going to drop on the floor. All the devices are T-Mobile. Using HLR resources, I know that the phone calls themselves, or the phone number itself is going to be allocated to a T-Mobile network in the United States. So if I scan through HLR, I can eradicate anything like Sprint, Verizon, AT&T, all the networks that are not T-Mobile. So I can use that as a secondary resource. I know that if I send SMS to it, that if I don't get an error from the network saying SMS isn't available, then it's probably, you know, obviously SMS being part of the GSM is not going to be disabled, but just to point out that sometimes you do get error messages, there are anomalies in the network based on routing issues, where, you know, you get dropped into a particular part of the network where SMS is not allowed for whatever reason, and then they say, okay, there's some kind of error coming back to you. So you can use that as a test as well. The NPA NXX, interestingly enough, when T-Mobile allocates a SIM for an embedded device, the embedded device, even though you purchase it in, say, New York, will actually have an NPA NXX in the SyScan or phone number allocated for a completely different region. Okay? So it won't be allocated for New York. It'll be someplace like Los Angeles or, you know, Houston, Texas, or someplace random like that. So what was cool is back when HLR actually showed the mobile switching center value, you could determine whether or not that person's location was the same as their NPA NXX. In the Carmen San Diego project that I was involved in last year, we proved that we could use the MSC value, reverse engineer it, in the United States and determine somebody's location, physical location, just based on that value alone. So we would have been able to actually use that value to determine, oh, hey, this person's location isn't the same as the NPA NXX, and if I pull it over a month's time, it never is. So that could be an embedded device that was allocated to somebody that lived in some other state, right? Unfortunately, due to our research, T-Mobile actually secured the HLR so that you can no longer pull location information over HLR, which is good for privacy, but it's bad for researchers, right? Because it obviously closes a hole for us. So unfortunately, it was a bug that was killed, and that's kind of a sad thing. The caller ID is also a great way to fingerprint. So we figured out a way to spoof back to our own PBX to pull caller ID information from the upstream provider. And if it's unavailable, typically that means that if it's a GSM network, like AT&T or T-Mobile in the US, there should be a billable allocation for that number unless they specifically asked not to. And in the case of T-Mobile, you can ask them many times, I don't want my information published with caller ID. And a lot of times they won't listen to you. They'll just put it in there anyway. So if it actually says unavailable, it means two things: burner or embedded device. And usually if it's a burner, you know, obviously there's going to be a person attached to that phone. So all the device profiles are going to fail. All those tests that you use in the device profile are going to fail. It's going to say, yeah, this is definitely not an embedded device. right? Because it can accept calls, it can accept SMS. It's, there are other features that are associated with a person instead of a device. So the whole point of device profiling is to make it less intrusive, okay? So instead of blasting out 100,000 messages all over the place, you simply device profile, and then you know that you're sending specific messages to specific devices that have a high probability of matching your embedded device. And that's very important because the networks themselves actually watch the incoming messages to determine if somebody's targeting resources on their network. And then they'll adjust the network to correspond to mitigations for that specific threat. And we've seen this over time, especially on the T-Mobile network, where they'll actually correctly mitigate specific attacks when they're seeing that, somebody's trying to flood SMS to activate this specific device. So we'll change the routing information so that it can't come from this provider and drop those types of packets for a specific amount of time. Other SMS types, similar types of messages will come through, but generally the types of messages that are going to be relating to that specific device will fail. It's very interesting. I don't know exactly how they're configuring, whether it's SS7 firewall, et cetera, because this is all black box. I've talked to some of the CSOs of these companies, and they've assured me that it's mostly SS7 firewalls that are doing these kinds of jobs, but it's actual people looking at logs that are determining what devices are being attacked, how they're being attacked, and whether or not they can do some kind of tweak in the firewall to mitigate that control. So the less you're sending those messages, the better, right? That's the whole point here, is that you have to pick and choose your battles. And especially in war texting, the less battles you take on, the more you're going to win. And device profiling is what that's all about. So we can find and target users, right? Because now we know that we can send device messages, okay? We can force the devices to come to us. And now we have a technique to scan 100,000 or more, however many phone numbers, to look for specific device profiles, so we're not getting blocked or getting mitigated by the provider. So we know that we can force devices to come to us in a very stealthy fashion. But what can we do? Can we impersonate? Obviously. Of course we can. We can impersonate. You know that we can impersonate because those slides that we showed at the very beginning of the talk showed me in Afghanistan and Libya. Obviously I wasn't there, right? If we know that those payloads shipped over serial are all in the clear, there's no confidentiality whatsoever, then we know we can spoof, right? Because the only tokens are what? The location information, the location nonce, loc34 dash whatever, and the phone number, okay? So the phone number itself, the location ID defines the user. That's the only information that this network gets. And again, this is not abnormal. This is totally normal for unmanned embedded devices on the cell phone network. Those are really the only resources that are available because the T-Mobile or AT&T or whatever network is never going to expose the resources on the SIM card to help authenticate that device to a third party. And ZoomBack is considered a third party, right? And that's what's so interesting about this because we know that the SIM card information is never going to be exposed. So the minimal amount of authentication tokens available are going to be the phone number, the equipment information, and some other specific information like a nonce sent over SMS or some other control. Things that we can control ourselves, right, as the attacker. We're going to be able to control those fields. So the interesting thing, getting back to the assisted part in AGPS, you're actually assisting them. So every time you're using an AGPS resource, they're learning about the cell phone network as you drive around, right, or walk around or what have you. That's the very cool thing about AGPS. AGPS allows a service provider to say, oh, hey, check out these new cell towers that just got installed in Denver, right, or just got installed in Taiwan, or whatever, right? They learn when the network changes and how the network changes. And what's interesting about this is they usually don't have access to that information. A lot of that information is proprietary, okay? And that proprietary data is being sold off, okay? So when these different networks associate with each other, they say, hey, I need your cellular data. I need to know where your towers are. I need to know the signal strength. And I need to know whether or not it's capable of these specific features. Well, the providers will sell that data as a database. So you have to pay for it. But if somebody is using a GPS, they can generate their own database using you as the user to make them money. Okay? So that's very cool because when you think about it, I showed earlier, remember, the GPS data isn't always sent, which is why a GPS information is necessary. So the AGPS data is going to define your location, and the GPS information is awesome if it's there, but it doesn't have to be there. We know that cellular information should always be there unless you're out in the middle of nowhere. But if we know this, we can actually mess up their database and corrupt it. And that's extremely important from an attacker's point of view, because now you can slowly change database entries to look like they're changing, right? Because the networks change. A network's going to tear down a cell tower in Denver, Colorado, and that, that cell ID is going to be moved somewhere else. That cell ID will be reallocated. Now the location area code should stay the same. Okay, the location area code is a general location area code for, say, a city or a part of a city or some greater area. But the cell ID will move to a different location. Well, these guys aren't really that slick, right? AGPS isn't that smart. They're going to take in the cellular information and start saying, oh, that's weird. The cell tower, or the set of cell towers that used to be in Denver, Colorado, is suddenly showing up in Libya. That's weird. And then suddenly when they don't get GPS information and they just get cellular information, now if they've got enough hits, right? They've got enough hits in that database to make it more probable that these cell towers are in Afghanistan or Libya or wherever, they're going to start popping up Libya on the map. And so now you're completely ruining their ability to give individuals accurate information whatsoever, right? Because they can't know for sure. The information that's being shipped to them has absolutely no confidentiality and integrity. Their database is being populated by information that they can't verify. And it's being populated by information that can change. So they know that that information could possibly move, and you can use that information to abuse their system, and then readjust the way that people are perceiving the information that they're being given. So if you take one of their targets and move it from Denver, Colorado to Orlando, Florida, but then you change the cellular information by pounding their database over and over and over with the AGPS data, it's going to look like the cell towers for Orlando are actually in Denver or vice versa. So the GPS information no longer matters because the biggest hit is going to be the cellular data. So now we have everything, right? We have the ability to intercept information from devices. We have the ability to uncover devices randomly on the net and find their location. And we have the ability to impersonate. So what can really be done here? This is the big deal, right? Tracking information today is a huge, huge interest to security researchers. And I'm sure to private individuals as well. Because it's becoming ubiquitous. We're seeing technology everywhere that just enhances our lives by giving us access to information, giving us other people access to where we are and our resources are. But at the same time, it's exposing a lot of things, making us more vulnerable in the physical world, which is obviously, that's always a danger when technology is crossing over into the physical world. Devices like these and other embedded devices that can be tracked easily are directly affecting the threat model for the physical human being, right? And it's going to only get worse from here because devices are becoming more and more robust, but the security availability on these systems, the security surface on these systems, is still very small. And that's due to cost, right? So we can actually discover targets that are highly, highly desirable, depending on whatever your attack model is, right? Whether it's medical equipment traveling across the United States, somebody tracking a shipment of, whatever. There's actually, so one thing I didn't really want to get into because it's kind of weird, is the device itself is, okay, so it's manufactured by Zoomback, but they get a lot of the resources from a company called Holux, which some of you may be familiar with because they do a lot of business in Asia. So Holux manufactures a lot of the software that they use, and they OEM it, re-engineer it, and then deploy it. Okay? But a lot of the base software is Holux based. And what's interesting about that is Holux uses very similar software to manage something extremely interesting, which is offenders. And this is ankle bracelets, right? So very similar software is being used in ankle bracelets to track offenders from their homes, to determine whether or not they're still in their home. And obviously, if it's this easy to hack this device, it's probably going to be just as easy to attack that device, except there are going to be some hardware constraints in the way. Right? But that shows you that these devices are kind of a gateway into some very serious physical security issues. So fixing these problems is a seriously difficult thing. T-Mobile is doing it the very wrong way. And I noted that earlier when I was talking about the way that they're actually stopping incoming messages from allocating or from being allocated and routed to specific devices, unless the source number is correct, or MSISDN or shortcode or what have you. They're doing this incorrectly, obviously, but they also recently changed to a new model that's doing things even more crazily, right? So now they're using geographic unroutable networks. So say you have a phone number 544-212-XXXX. That NPA and XX, or the exchange and area code, is actually going to not be routable overseas. Even though it's GSM, even though that phone number is attached to the GSM network, even though it's attached to all other GSM networks within the United States, it's routed only within the United States and not without. Okay? So what's really cool about that is that T-Mobile thinks that they've won when they haven't won at all. So obviously you just get an SMPP that's within the United States, or you just use another device within the United States that's accessible. Like you can route between AT&T and T-Mobile very easily, bypassing all of this. So you just start sending messages, binary messages from those devices, right? So that's not a protection at all. That's only a protection from the spammers overseas in the EU, where most of the SMPP companies are. But it's not a real protection. It's not a real mitigation, right? So they're going to have to rethink that. The other issue is PDB context. So when you drop into GPRS, your PDB context, so your network routing information, is determined from your SIM identity, the routing information from the GPRS network once you attach, and some other information that's defined within the GPRS network itself. So obviously the only identity issue there, and the equipment information from your phone. But what's interesting about that is that obviously if you have an unlocked phone, it doesn't really matter what the information being sent from your phone is. T-Mobile thinks everything that's unlocked is the same kind of device. So PDB context is unnecessary and a really bad protection, because if it's unlocked, you can drop it at any PDB context using the correct SIM. Right? So if the SIM has access to that PDB context, there's no other information. It can't say, yes, it's definitely this Zubac device, or yes, it's definitely a Kindle, or whatever. It's just going to see the SIM card, the unlocked capabilities of that device is going to then say, hey, I am this particular device, or I am no device, or I can't be defined. And then the equipment identity no longer matters, and the phone gets put into a particular mode on the PDB context in the GPRS network, along with every other device that's supposed to be on that network. So it's not rerouted. Okay? So that's obviously a very insufficient protection. But what they should be doing is obviously not even using IPv4 addresses embedded in SMS in the first place. Right? That's a very dangerous thing, to define location or a destination address in an SMS payload. That's ridiculous. Nobody that we know would ever do something like that, right? That's just not smart. But they do this, and not only this device, but many other devices that are controlled over SMS, because they have to be dynamic. And it's very difficult to constantly upgrade these devices. And if the network changes, if the GPRS network changes, the GSM network changes, they have to be versatile enough to be able to connect to different types of networks and still ensure that the information is being sent to the appropriate host. So it's reasonable that this information would occur, or that this information would occur within a packet sent to a device. It's understandable from an engineering point of view when it comes to GSM networks, but it's really not smart for obvious reasons that we've seen here, right? There's no semblance of confidentiality and integrity. Of course, this is something that needs to be changed. And we're going to see that more as embedded devices get more robust. But this is an issue of just embedded development in the first place. Obviously, if Sony and the PS3 can't do it correctly, how are people using this kind of a minimalistic architecture going to be able to do it correctly? It's not going to happen. It's just not going to happen. The money isn't there. The device robustness is not there. It's not available. So one very easy thing that they can do very quickly is just allowing zoom back devices to talk to non-zoom back devices. So when I connect to the GPRS network, I'm using a GSM modem, right? I'm not using an actual zoom back device. I just throw the SIM card in a GSM modem that's unlocked and connect to T-Mobile. It drops me in the right P2P context, and now I can talk to other zoom back devices, even though I'm not one. But they don't know that. They don't know what devices connecting to their network are zoom back or not. Just the same with any other embedded network provider. Well, what they can do is force the routing to occur within that network to go through an external set of hosts on a different subnet, so that nobody can directly route to anybody else on the same subnet. So even if I tried to talk to somebody on a 10/8, it would never happen, right? Because the routing and the firewalling would force me to pass through some other, secondary tier network that would then decide whether or not I could perform that action, and then just drop the packet on the floor if I attempted to do something I shouldn't be doing. So that's very easy. Another cool trick would have been to use the Carmen Sandiego project to actually investigate HLR and say, oh, hey, HLR shows that the device is actually in Denver, Colorado, whereas the GPS location coming back over GPRS is saying that the device is in Orlando, Florida. You could have been able to use that as a secondary way of accessing the information through the actual routing infrastructure. But because we've closed that hole, that means that T-Mobile is actually going to have to export that information to you, and they're never going to do that. They're not going to do that anymore, because that to them is as proprietary, almost as proprietary, as your SIM data. Okay? And that's just information they don't want to give up. So, because I'm running out of time, I'll just go ahead and skip this, because I've already described the